Next theorem. Let A be an n by n square matrix. When two adjacent rows are interchanged, the determinant of the new matrix is negative determinant of A. What this theorem says is that A is an n by n square matrix. For example, if I can let A be a 3 by 3 square matrix. 1, 2, 3, 4, 0, 6, 0, 7, 9. For example, that's matrix A. If I interchange two adjacent rows, for example, I can change the first row and the second row, or the second row and the third row. If I interchange the second row and the third row, I have a new matrix 1, 2, 3, 0, 7, 9, 4, 0, 6. If I interchange the second row and the third row, I have a new matrix. Let me call this new matrix B. Then this theorem says the determinant of the new matrix is negative determinant of A. That's what this theorem says. We interchange two adjacent rows. The determinant of the new matrix is negative determinant of A. We can verify this by yourself. You can verify this by yourself. But an example is not proof. This is an example. An example is not proof. Next, let's prove the theorem. Let A be an n by n matrix when two adjacent rows are interchanged. So assume the ith row and I plus 1th row are interchanged. In matrix A are interchanged. Assume the ith row and I plus 1th row are interchanged. In matrix A are interchanged. Suppose this is matrix A. First row is A11, A12, A1n. That's the first row. Second row is A21, A22, A2n. That's the second row. Continue, we'll have an ith row. And entry in the ith row is AI1, AI2, and AIN. Next row will be I plus 1th row. Next row will be I plus 1th row. Continue, the last row will be the nth row. AN1, AN2, ANN. The entry in the I plus 1th row, I can write it as AI plus 1, comma 1, AI plus 1, comma 2, AI plus 1, comma n. Now, if I interchange the ith row and I plus 1th row, what do I get? If I interchange row I and row I plus 1, I have a new matrix. I get a new matrix here. If I interchange row I and row I plus 1, I get a new matrix. Where the first row stays the same, second row stays the same, I interchange the ith row and I plus 1th row. So these two rows will be interchanged. In the ith row, I have AI plus 1, comma 1, AI plus 1, comma 2, and AI plus 1, comma n. That's the ith row. Then I put the ith row in I plus 1th row. I get AI1, AI2, AIN. Last row will be AN1, AN2, and ANN. That's a new matrix. Let me call this new matrix B. Let me call this new matrix B. I try to show that determinant of the new matrix equal to negative determinant of A. Next, let's find the determinant of the new matrix. Determinant of B. For determinant of B, we can find a coefficient expansion along any rows or any columns in matrix B. Here, let me find a coefficient expansion along the I plus 1 row. Here, let me find a coefficient expansion along the I plus 1 row. And we know that for coefficient expansion, the sign of the coefficients is alternating. The sign of the coefficients is alternating. It could be plus, minus, plus, minus, plus, minus, plus, minus, plus. The sign of the coefficients is alternating. So for the first entry here, since we don't know if I is even or odd, we can't tell if this sign is positive or negative. So for the sign, let's leave it as -1 to the power of I plus 1 plus 1. That's the I plus 1 row and first column. So I plus 1 plus 1. The entry is AI1 times determinant of the submatrix of matrix B. For determinant of the submatrix, I cross out the I plus 1 row and the first column. Cross out the I plus 1 row and the first column. So that's the determinant of the submatrix from matrix B by removing the I plus 1 row and the first column. Next entry. We don't know if I is positive or negative. We don't know if the sign is positive or negative because we don't know if I is even or odd. So we leave it as -1 to the power of I plus 1 plus 2. That's an I plus 1 row in the second column times the entry A sub I2 times determinant of the submatrix. Determinant of the submatrix of matrix B by removing the I plus 1 row in the second column. That's a submatrix of matrix B by removing the I plus 1 row in the second column. Continue. In the last entry here, that's in the I plus 1 row in the nth column. That's in the I plus 1 row in the nth column. From the sign is -1 to the power of I plus 1 plus n times the entry A sub in times determinant of the submatrix. That's the submatrix of matrix B by removing the I plus 1 row and the nth column. That's the determinant of matrix B. Next, let's try to simplify. Let's try to rewrite the submatrix in terms of matrix A. Let's observe matrix A. In the ith row, for the first entry here, if I remove the ith row and the first column, that's the submatrix. Now in matrix B, if I remove the I plus first row and the first column, I got this submatrix. If we compare these two submatrices, we can see that they are exactly the same. Since I remove the row that contains AI1, AI2, AIN, I remove the row AI1, AI2, AIN, and also I remove the first column. The submatrix is exactly the same. So I get -1 to the power of I plus 1 times AI1 times determinant of the submatrix. This submatrix in matrix B, if I remove an I plus 1 row and the first column, that's exactly the same as the submatrix in matrix A. If I remove the ith row and the first column, what I remove is exactly the same row, and the rest of the rows have exactly the same order. So that's the same as the submatrix in matrix A by removing the ith row and the first column. If I remove an I plus 1 row in matrix B and the first column, I remove an ith row in matrix A and the first column, the submatrix is exactly the same thing. First row, second row, third row, I plus 1 row, n row. First row, second row, I plus 1 row, and n row. Since I remove the same thing, what's left is exactly the same. Exactly the same submatrix in the same order. So they're exactly the same here. Since they are adjacent rows, if I remove one of the row, it won't affect the order of other rows. Next, same thing, I plus 1 plus 2. Negative 1 to the power of I plus 1 plus 2. Times entry AI2 times determinant of the submatrix. The submatrix Bi plus 1 comma 2. That means in matrix B, I remove an I plus 1 row and a second column. That's exactly the same as the submatrix in matrix A. I remove an I row in the second column. Because I and I plus 1 are adjacent rows, there's no row in the middle. If I remove this row, the order of the other rows stays exactly the same. So these rows have exactly the same order. If I remove an I row and I plus 1 row, the other rows has exactly the same order. Plus plus negative 1 to the power of I plus 1 plus n times AIN times determinant of the submatrix. The submatrix of matrix B by removing the I plus 1 row and the nth column. It's exactly the same as the submatrix in matrix A by removing the ith row and the nth column. So this is exactly the same as the submatrix in matrix A by removing the ith row and the nth column. So let's simplify matrix B, determinant of B. I write the submatrix in terms of matrix A. Next, continue. If you observe the sign here, every term contains the extra 1, contains I plus 1, I plus 1, I plus 1. If I pull out this 1, if I pull out negative 1, what's left is negative 1 to the power of I plus 1 times AI1 times determinant of the submatrix of matrix A by removing the ith row and the first column. Here I can pull out negative 1 of negative 1 from each term. I pull out 1 of the negative 1 from each term. Next term is negative 1 to the power of I plus 2. I take out this 1, negative 1 to the power of 1. Times AI2 times determinant of the submatrix of matrix A by removing the ith row in the second column. Then same thing here. I pull out this 1 here. I pull out negative 1 to the power of 1 here. So in the last term I have negative 1 to the power of I plus n times AIN times determinant of the submatrix of matrix A by removing the ith row and nth column. Then, if you observe what's in the bracket here, that's the coefficient expansion of matrix A along the ith row. What's in the bracket is the coefficient expansion in matrix A along the ith row. So, negative 1 to the power of I plus 1 times the entry AI1 times determinant of the submatrix of matrix A by removing the ith row and the first column. Negative 1 to the power of I plus 2 times the entry AI2 times determinant of matrix A by removing the ith row and second column, and so on. That's determinant of matrix A along the ith row. So this is the same as determinant of A. That completely proves that determinant of B, determinant of the new matrix, equal to negative determinant of A. So that completely proof. Next theorem. Let A be an m by n square matrix. When any two rows are interchanged, the determinant of the new matrix is negative determinant of A. This theorem looks very similar as the previous theorem. The previous theorem says when two adjacent rows are interchanged, the determinant of the new matrix is negative determinant of A. This theorem says when any two rows are interchanged, the determinant of the new matrix is negative determinant of A. How can we prove this theorem? Let's look at an example first. Let A be be a 7 by 7 square matrix. For example, let A be a 7 by 7 square matrix. And then the row vectors be R1, R2, R3, R4, R5, R6, R7. Then these be the row vectors R1, R2, R3, R4, R5, R6, R7. So that's the row vector in the first row. That's the row vector in the second row. That's the third row. That's the fourth row. That's the fifth row. That's the sixth row, and that's the seventh row. Now think of this question. If we want to interchange the second row and the fifth row by only switching two adjacent rows, by only switching two adjacent rows, by only switching the adjacent rows, how many switches does it take? Think of this question. If we want to interchange the second row and the fifth row by only switching adjacent rows, how many switches does it take? If we try to interchange row 2 and row 5 by only switching adjacent rows, how many switches does it take? Let's try. I can first of all switch row 2 and row 3. That's one switch. I can first of all switch row 2 and row 3. I get R1, R3, R2, R4, R5, R6, R7. Next, I can switch row 2 and row 4. Switch row 2 and row 4. They are the adjacent rows. I can switch row 2 and row 4. They are adjacent rows now. They are adjacent rows. I can switch row 2 and row 4. I get R1, R3, R4, R2, R5, R6, R7. Next, I can switch row 2 and row 5. Now they are adjacent rows. I can switch row 2 and row 5. I can switch row 2 and row 5. Now they are adjacent rows. I can switch row 2 and row 5. I get row 1, row 3, no, row 4, row 5, row 2, row 6, row 7. Now I move here. I move row 2 to the fifth row. Here I move row 2 to the fifth row. It takes me 3 switches to move row 2 to the fifth row. It takes me 3 switches to move row 2 to the fifth row. Next, I try to move row 5 to the second row. Next, I try to move row 5 to the second row. So next, I will interchange row 4 and row 5. Now the adjacent rows here. I'll switch row 4 and row 5. I switch row 4 and row 5. If I switch row 4 and row 5, I get row 1, row 3, row 5, row 4, row 2, row 6, row 7. Now, row 5 and row 3 they are adjacent rows. I can switch row 5 and row 3. If I switch row 4 and row 3, I get a matrix R1, R5, R3, R4, R2, R6, R7. Now I complete the interchange. I interchange row 2 and row 5 completely and leave the rest the same. I interchange row 2 and row 5 and leave the rest the same. So here we can see that it takes 3 switches to move row 2 to the 5th row. It takes 3 switches to move row 2 to the 5th row. Then it takes 2 switches to move row 5 to the 2nd row. Then it takes 2 switches to move row 5 to the 2nd row. So first of all, it takes 3 switches to move row 2 to the 5th row. Then it takes 2 switches to move row 5 to the 2nd row. And here you can see that if we want to change row 2 and row 5, the difference between 2 and 5 is 3. It takes 3 switches to move row 2 to the 5th row. And then it takes 2 switches to move row 5 to the 2nd row. So in general, based on this example, we know that in general, if we want to interchange row I and row J, by only switching adjacent rows, assume K is the difference between I and J. Assume K is the difference between I and J. Then we know that it takes K moves. It takes K switches. It takes K switch to move Ri to the Jth row. And it takes K minus 1 switches to move Rj to the ith row. So it totally takes K plus K minus 1 to interchange row I and row J by switching only 2 adjacent rows. So it takes a total of K plus K minus 1 switches to interchange row I and row J by switching only adjacent rows. only switching adjacent rows. Based on this example here, let's prove this theorem. Let A be an m by n square matrix where any two rows are interchanged. The determinant of the new matrix is negative determinant of A. Let's prove it. Let A be an m by n square matrix with row vectors R1, R2, Rn. When row Ri and Rj are interchanged, when Ri and Rj are interchanged, let B be the new matrix. When ith row and jth row are interchanged, let B be the new matrix. And let K be the difference between I and J. Let K be the difference between I and J. Now, let A be the matrix with row vectors R1, R2, Ri, Ri plus 1, Rj minus 1, Rj, Rn. Let A be a m by n matrix with these row vectors. That's the first row. That's the second row. That's the ith row. Next is I plus 1 row. Next is j minus 1 row. That's the jth row. And the last row is the nth row. If we try to interchange row I and row j by only switching adjacent rows, we know that it takes k moves, it takes k switches to move Ri to the jth row. So take k switches to move Ri to the jth row. R1, R2 stays the same. If I interchange, it will be Ri plus 1 here, Ri plus 2, after interchanging, eventually Ri will be here, Rj will be here. That's Rn. So take k switches to move Ri to the jth row. Next, it takes k minus 1 switch to move Rj to the ith row, assuming we only switch adjacent rows. It takes k minus 1 switches to move Rj to the ith row. We get the matrix R2, R1, R2, Rj, Ri plus 1, Rj minus 1, Ri, Rn. This is matrix B. So from matrix A to matrix B, it takes a total of k plus k minus 1 switches. So if we only switch adjacent rows, we can see that it takes k switches to move row I, Ri, to the jth row. And it takes k minus 1 switches. It takes k minus 1 switches to move Rj to the ith row. So it takes a total of k plus k minus 1 is 2k minus 1. K plus k minus 1 is 2k minus 1. It takes a total of 2k minus 1 moves, switches, to interchange row I and row j. So we take a total of 2k minus 1 switches to interchange row I and row j. By the previous theorem, we know that every time when we switch two adjacent rows, the sign will be switched. The sign of the determinant will be switched. Then, by the previous theorem, we know that every time when we switch two adjacent rows, the sign of the determinant will be switched. So, from matrix A to matrix B, it takes 2k minus 1 switches. So the sign will be switched 2k minus 1 times. It will be negative 1 to the power of 2k minus 1 times determinant of A. Every time when we switch two adjacent rows, the sign will be switched. Since we switch adjacent rows 2k minus 1 times, the sign will be switched 2k minus 1 times. So determinant of B equal to negative 1 to the power of 2k minus 1 times determinant of A, which is negative 1 raised to R power must be negative 1. Negative 1 raised to R power must be negative 1. 2k minus 1 is R power. So determinant of B equal to determinant of A. That complete the proof. Note, for this theorem, we can memorize like this. support of a matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. If I interchange any two rows, for example, I interchange the first row and the third row. If I interchange any two rows, we're going to take determinant equal to negative determinant of an original matrix. If I interchange any two rows, equal to negative determinant of an original matrix. These two bars means determinant. These two bars means determinant. Or we can also think of that when we interchange any two rows, the sign of the determinant switched. When we interchange any two rows, the sign of the determinant will be switched. When we interchange any two rows in a matrix, the sign of the determinant will be switched. Next theorem, let A be an n by n square matrix. If any two rows in matrix A are proportional, then determinant of A is 0. How can we prove this theorem? Let's set down a problem first. Let A be an n by n square matrix. With row vectors R1, R2, and Rn. Let A be an n by n square matrix with row vectors R1, R2, and Rn. Assume the ith row and the jth row are proportional. So assume the ith row equal to k times the jth row. Assume the ith row and the jth row are proportional. Assume the ith row equal to k times the jth row. Then A can be written as R1 in the first row, R2 in the second row. That's the ith row. That's the jth row. And that's the nth row. Since the ith row and the jth row are proportional, I can replace Ri with k times Rj. Since the ith row and the jth row are proportional, I can replace Ri with k times Rj. Next, let me introduce matrices B and C. Let B be the matrix obtained from matrix A by interchanging the ith row and the jth row. So if I interchange the ith row and the jth row, everything else stays the same. So first row is R1, second row is R2, the ith row will be Rj, and the jth row will be k times Rj, the nth row will be Rn. That's matrix B. And let C be the matrix obtained from matrix A. Let C be the matrix obtained from matrix A by removing k from the ith row. Everything else stays the same. Only remove k from the ith row. I get R1, R2, Rj, Rj, Rn. That's matrices B and C. Now, what's their relationship here? Let's compare matrices A and B first. if we compare matrices A and B, we can see that the only difference is that the ith row and jth row switched. And we know that by the previous theorem, if we interchange two rows in a matrix, then the determinant of the matrix, the sign of the determinant of the matrix will be switched. So the sign of the determinant of the matrix will be switched, which means determinant of the new matrix B equal to negative determinant of A. If I interchange two rows in a matrix, the sign of the determinant will be switched. So determinant of B equal to negative determinant of A by the previous theorem. Next, let's consider determinant of A. When we're taking determinant for matrix A, we can see that in the ith row, there's a constant k. According to the earlier theorem, we know that when we're taking determinant for matrices, if there's a constant multiple in a row, I can always pull out a constant multiple. So pull out k. So when we take determinant for matrix A, if I pull out k from the ith row, what's left is this matrix. This matrix is the same as matrix C. If I pull out k, the resulting matrix is the same as matrix C. So that equal to k times determinant of the resulting matrix. And the resulting matrix is matrix C. And similarly, if we consider determinant of matrix B, when we take determinant for matrix B, in the jth row, there's a constant multiple k. According to this theorem, to the earlier theorem, we know that if there's a constant multiple in a row, when we're taking determinants, we can always pull out a constant multiple from the row. So in matrix B, if I pull out a constant multiple from the jth row, the resulting matrix is the same as matrix C. They are the same everywhere except the jth row. They are the same everywhere except the jth row. So in the jth row, if I pull out k, then matrices B and C will be exactly the same. So if I pull out k, the resulting matrix is matrix C. So determinant of B equal to k times determinant of C. Here, since both determinant of A and determinant of B, they both equal to k times determinant of C, then determinant of matrix A and B must be exactly the same. So they are the same. Since determinant of A and B they are exactly the same, I can replace determinant of B with determinant of A. Since they are exactly the same, I can replace determinant of B with determinant of A. So determinant of A equal to negative determinant of A. Then I can add determinant of A to both sides. I get twice determinant of A equal to 0. I can add determinant of A to both sides. I get twice determinant of A equal to 0. Then I can divide both sides by 2. If I divide both sides by 2, determinant of A is 0. That complete the proof. So in a matrix A, if any two rows are proportional, then the determinant of A must be 0. Next, based on the previous theorem, we have a following corollary, which says, in a square matrix A, if any two rows are identical, then determinant of A must be 0. The proof is simple. In matrix A, if two rows are identical, then their proportion is 1. By the previous theorem, if any two rows in a matrix A are proportional, then determinant of matrix A must be 0. By the previous theorem, determinant of A must be 0. These two rows are proportional. Next theorem, let A be an m by n square matrix. When a row is multiplied by a scalar k and added to a different row, the determinant of the new matrix is the same as determinant of A. How can we prove it? Let's set out the problem first. Let A be an n by n square matrix. With row vectors R1, R2, up to Rn. Assume the jth row is multiplied by a scalar k. Assume the jth row is multiplied by a scalar k and add it to the ith row. Assume the jth row is multiplied by scalar k and add it to the ith row. Consider the following matrices A, B, and C. So here, A is the matrices. A is the matrix with row vectors R1, R2, Ri in the ith row, Rj in the jth row, and the last row is Rn. Also that's matrix A. Also that's matrix A. If we multiply the jth row by k and add it to the ith row, what do we get? If we multiply the jth row by k and add it to the ith row, what do we get? We get Ri plus k times Rj. If I multiply the jth row by k, add it to the ith row, I get Ri plus k times Rj in the ith row. I multiply the kth row, I multiply the jth row by k, then add it to the ith row, I get Ri plus k times Rj. And the rest of the rows stays the same. First row is R1, second row is R2, that's the ith row. The jth row is the same as Rj. Everything stays the same. And the last row is Rn. That's the new matrix. That's the new matrix after I multiply a row by a constant, add it to a different row. That's a new matrix. Let me call this matrix C. Let me call this matrix C. Next, let's consider a matrix B. Let's consider a matrix B. Matrices A and B are the same everywhere except the ith row. Consider matrix B. Matrices A and B, they are the same everywhere except the ith row. They are the same everywhere. Except the ith row. In the ith row, I write krj here. In the ith row, I write krj here. So matrices A and B, they are exactly the same everywhere except the ith row. In the ith row, I write krj here. Now, let's compare matrices A, B, and C. Every row is identical. Every row is identical except the ith row. Matrices A, B, and C. In matrices A, B, and C, every row is identical, except the ith row. In the ith row, the sum of the row vectors in matrix A and B, the sum of these two row vectors in matrix A and B, is the same as the row vector in matrix C. According to an earlier theorem, we know that if matrices A, B, and C, the entries is the same everywhere except the ith row, and the sum of the ith row vector in matrices A and B equal to the ith row vector in matrix C, then determinant of matrix C equal to the determinant of A plus determinant of B. That's earlier theorem. So if in matrices A, B, and C, the entries are the same everywhere except the ith row, and the sum of the ith row vector in matrices A and B, the sum of their row vectors in the ith row, is the same as the row vector in matrices C, then determinant of C equal to determinant of A plus determinant of B. Since in matrices A, B, and C, the entries are the same everywhere except the ith row, and in the ith row, the row vectors in matrices A and B, the sum of the row vectors in matrices A and B is the same as the row vector in matrices C. Ri plus Krj equal to Ri plus Kij. Then, by earlier theorem, we know that determinant of C equal to determinant of A plus determinant of B. We try to show that, in this theorem, determinant of C equal to determinant of A. Determinant of a new matrix is the same as the determinant of matrix A. How can we prove that? Let's observe matrix B. Let's observe matrix B. In matrix B, the ith row and the jth row are proportional. In matrix B, the ith row and the jth row are proportional. Then, according to the previous theorem, in a matrix, if any two rows are proportional, determinant of the matrix is 0. So, by the previous theorem, determinant of B is 0. Hence, determinant of C equal to 0 equal to determinant of A plus 0. So, determinant of C equal to determinant of A. So, determinant of the new matrix equal to determinant of A. That complete the proof. Determinant of the new matrix equal to determinant of A. That complete the proof. Note: for this theorem, we can memorize like this. Suppose we have a matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. If I multiply a row by a constant and add it to a different row, for example, I multiply the third row by k added to the first row, I get A11 plus k times A31, A12 plus k times A32, A13 plus k times A33. If I multiply a row by a constant, add it to a different row, and leave the rest the same, then the determinant of the new matrix is the same as the determinant of the old matrix. If I multiply a row by a constant and add it to a different row, the determinant stays the same. That's what this theorem says. Also, keep in mind that for all above theorems, if we change rows to columns, the theorems are also true. For example, in the earlier theorem, we say that let A be an m by n matrix, let k be a scalar. When k is multiplied to a row in A, if I change it to column in A, when k is multiplied to a column in A, then determinant of new matrix is k times determinant of A. If I change the row to column, this theorem is also true. So if I multiply a column by a constant, I can also pull on a constant from the matrix when I take determinant. And also here, for this theorem here, let A be an m by n square matrix. When any two rows are interchanged, if I change rows to column, when any two columns are interchanged, the determinant of the new matrix is negative determinant of A. So if I interchange two columns in a matrix, then the sign of the determinant will also be switched. And for this theorem here, let A be an m by n square matrix. When a row is multiplied by scalar k, added to another row, if I change the word row to column, the theorem is also true. If I say when a column is multiplied by a scalar k and added to a different column, the determinant of the new matrix is the same. So if I multiply a column by a constant added to a different column, the determinant of the matrix stays the same. So for all above theorems, if I change rows to columns, the theorem are also true. The proofs are very, very similar. Next, let me show you the relationship between determinant and elementary row operations. We know that there are three elementary row operations. We can multiply a row by a non-zero constant. We can interchange two rows. Or we can multiply a row by a constant and add it to another row. Those are three elementary row operations. When we are taking determinant, if I multiply a row by a constant, when we are taking determinant, if I multiply a row by a constant, it's the same as saying I take the constant times the determinant of the entire matrix. When we are taking determinant, if I multiply a row by a constant, it's the same as saying I take the constant times the determinant of the entire matrix. Or from the first formula, you can think of that. If there's a scalar multiple in a row, when we are taking determinant, if there's a scalar multiple in a row, it's the same as saying I factor the scalar multiple out. It's the same as saying I factor the scalar multiple out. So keep this rule in mind. When taking determinant, if there's a scalar multiple in a row, we can pull the scalar multiple to the front of the determinant. When we're taking determinants, when there's a scalar multiple in a row, I can pull the scalar multiple to the front of the determinant. That's first rule. Now, second operation here. When we're taking determinant, if I interchange two rows, the sign of the determinant will be switched. When we're taking determinant, if I interchange two rows, the sign of the determinant will be switched. So keep this rule in mind. When taking determinant, if any two rows are interchanged, then the sign of the determinant will be switched. If it's positive, we make it negative. If it's negative, we make it positive. If we interchange two rows, the sign of the determinant will be switched. That's the second rule. The third rule, when we are taking determinant, if I multiply a row by a constant added to another row, the determinant stays the same. When we are taking determinant, if I multiply a row by a constant, then added to another row, the determinant stays the same. That's the third rule here. When taking determinant, if we multiply a row by a constant and then add it to another row, the determinant stays the same. That's the third rule. Keep these three rules in mind. That's the relationship between determinant and elementary row operations. Next, let me show you an example. Find determinants for each of the following matrices using elementary row operations. How can we find determinant using elementary row operations? For example, for determinant of matrix A, how can we find determinant using elementary row operations? For determinant of matrix A, we have 3, 2, 4, -1, 6, -5, -3, 1, and 2. If we try to find determinant using elementary row operations, we try to make this matrix upper triangular. Then, for upper triangular matrix, we can multiply all entries in the main diagonal and get a determinant. So, how can we make this upper triangular? First of all, in the first row, try to make a leading one here first. How can we make one here? I can multiply second row by number 2, add it to the first row. I can multiply second row by 2, add it to the first row. If I multiply a row by a constant, add it to another row, determinant stays the same. -1, 6, -5. Multiply second row by 2, add it to the first row, I get 1. 14. 12 plus 2 is 14. -10 plus 4 is -6. Third row stays the same. Next, I try to make all entries below leading 1 to be 0. All I can do is I can multiply first row by 1, add it to the second row. Multiply first row by 1, add it to the second row. And then multiply first row by 3, add it to the third row. When we multiply a row by a constant, add it to another row, determinant stays the same. So first row stays the same, 1, 14, -6. Add first row to the second row, I get 0, 20, that's -11. Then multiply first row by 3, add it to the third row, I get 0. 3 times 14 is 42. 42 plus 1 is 43. Next, 3 times -6 is -18. -18 plus -2 is -20. Next, in the second row, try to find a leading one here. How can we make one here? It looks hard to make number 1 directly from on the second row. So all I can do is, at least I can make number smaller first. I can multiply second row by -2, add it to the third row, make number smaller first. If I multiply a row by a constant, add it to another row, determinant stays the same. Multiply first, second row by -2, add it to the third row, I get 3 here. -2 times 11 is 22. 22 plus -20 is +2. Next, I try to make 1 here. I multiply the third row by -7, add it to the second row, multiply third row by -7, add it to the second row. So leave the third row the same. -21 plus 20 is -1. -14 plus -11 is -25. Next, try to make 0 here. I can make second row by +3, add it to the third row. -1 is okay. The goal is making this matrix upper triangular. -1 here is okay. Multiply second row by 3, add it to the third row. If I multiply a row by a constant, add it to another row, determinant stays the same. Zero, 0, 3 times -25 is -75. -75 plus 2 is -73. Then this is an upper triangular matrix. This is upper triangular matrix. For upper triangular matrix, we can multiply the entries in the main diagonal. That's a determinant. 1 times -1 times -73, which is +73. That's a determinant of this matrix. Here we solve it using elementary row operation. We can also solve it using coefficient expansion. Answer will be exactly the same. Next, for matrix B, do the same thing. Determinant of matrix B. Try to make the matrix upper triangular. Apply row operation, try to make it upper triangular. 4, 1, 2, 3. 5, -6, 0, 7. 3, -1, 0, 6. 2, 9, -4, and 8. Apply row operation, try to make it upper triangular. What can we do here? Let's try to find a leading one here first. I can multiply the third row by -1, add it to the first row. If I multiply a constant to a row, add it to another row, determinant stays the same. So -1 times 3 plus 4 is +1. -1 times -1 is 1. 1 plus 1 is 2. -1 times 0 is 0. 0 plus 2 is 2. -1 times 6 is -6. -6 plus 3 is -3. The rest stays the same. 5, -6, 0, 7. 3, -1, 0, 6. 2, 9, -4, 8. The goal is to make a matrix upper triangular. So this is a leading one. Try to make all entries here to be 0. So all I can do is I multiply first row by -5, add it to the second row. Multiply first row by -3, add it to the third row. Then multiply first row by -2, add it to the fourth row. If I multiply a row by a constant, add it to another row, determinant stays the same. First row is 1, 2, 2, -3. Multiply first row by -5, add it to the second row, I get 0. -5 times 2 is -10. -10 plus -6 is -16. -5 times -2 is -10. -10 plus 0 is -10. -5 times -3 is 15. 15 plus 7 is 22. Next, multiply first row by -3, add it to the second row. I get 0 here. -3 times 2 is -6. -6 plus -1 is -7. -3 times 2 is -6. -6 plus 0 is -6. -3 times -3 is 9. 9 plus 6 is 15. Next, multiply first row by -2, add it to the fourth row. I get 0. Negative 2 times 2 is negative 4. Negative 4 plus 9 is 5. Negative 2 times 2 is negative 4. Negative 4 plus negative 4 is negative 8. Negative 2 times negative 3 is positive 6. 6 plus 8 is 14. Now move to the second row. Try to make the first entry to be a leading one. What can we do here? Next, I can try to multiply the 4 row by positive 3 and then add it to the second row. I can make a negative 1 here. So multiply the 4 row by positive 3. Add it to the second row. I can make a negative 1 here. When we multiply a row by a constant, add it to another row, determinant stays the same. So we get 1, 2, 2, negative 3. 3 times 4 is 15. 15 plus negative 16 is negative 1. 3 times negative 8 is negative 24. Negative 24 plus negative 10 is negative 34. 3 times 14 is 42. 42 plus 22 is 64. Leave the third row the same. Leave the fourth row the same. Getting a negative 1 is okay here. Since we try to make the matrix upper triangular, getting a negative 1 is okay. Next, I can multiply second row by 7. Multiply second row by negative 7, add it to the third row. And multiply second row by 5, add it to the fourth row. When we multiply a row by a constant, add it to another row, determinant stays the same. So first row stays the same, 1, 2, 2, negative 3. Second row is 0, negative 1, negative 34, 64. 0. Negative 7 times negative 1 is positive 7. Positive 7 plus negative 7 is 0. Negative 7 times negative 34 is positive 238. 238 plus negative 6 is 232. Negative 7 times 64 plus 15. Here I use my calculator. I get negative 433. Next, multiply second row by 5. Add it to the fourth row. I get 0. 5 times negative 5 is negative 5. Negative 5 plus 4 is 0. 5 times negative 34 is negative 170. Negative 170 plus negative 8 is negative 178. Next, take 5 times 64. That's 320. 320 plus 14 is 334. Next, in the third row, try to make a leading one here. Since both numbers are very, very large, it's hard to make leading one here. So what I can do is I can divide the third row by 232. Divide the third row by 232. There's no better way to do this. Divide the third row by 232. If I divide the third row by 232, think of I pulling out 232 from the third row. If I pull out 232 from one row, that's 232 times determinant of the matrix with 0, 0, 1, and negative 433 over 232. Think of this, I pull a constant from one row. It's the same as saying taking this constant, multiplied by the entire determinant. If I pull a constant multiple from one row, it's the same as saying taking the constant, multiplied by the determinant of the entire matrix. Here I pull out 232 from the third row. The rest stays the same. 1, 2, 2, negative 3. 0, negative 1, negative 34, 64. 0, 0, negative 178, 334. Next, I can multiply the third row by 178, add it to the fourth row. multiply the third row by 138, add it to the fourth row. So when I multiply a constant to a row, add it to another row, determinant stays the same. And this 232 stays there. This 232 stays there. I get 1, 2, 2, negative 3, 0, negative 1, negative 34, 64, 0, 0, 1, negative 433 over 232, 0, 0, 178 times 1 plus negative 178 is 0. Then the last entry here is 178 times this number. The last entry here is 178 times this number, negative 433 over 232 plus 334. Here I use my calculator. In my calculator, I get 207 over 116. So that's 207 over 116. That's the upper triangular matrix. That's the upper triangular matrix. So for determinant of an upper triangular matrix, I multiply the entries in the main diagonal. So leave 232 the same. For determinant of this upper triangular matrix, multiply all entries in the main diagonal. I get 1 times negative 1 times 1 times 207 over 116. 232 divided by 116 is 2. So I get 2 times 207, which is 414. And this number is negative. Positive number times negative number is negative. So determinant of this matrix is negative 414. So here you can see that when we try to find determinant of a matrix, we can either use coefficient expansion or we can use elementary row operations. Either way is okay. So that's another choice for us. Next example, assume the determinant of the matrix A, B, C, D is 7. Find each of the following determinants. How can we find determinant for these matrices here? Let's observe this matrix. They all look similar to the given matrix. So we can try to apply some row operation on each matrix, make it look like the given matrix, and then we can find the determinant. So for the first matrix, 2A, 2B, C, and D. Here we see that in the first row, there's a constant multiple 2. There's a constant multiple 2. According to the first rule here, if there's a constant multiple in a row, I can always pull out a constant multiple, put it in the front of the determinant. So I can pull out a constant multiple 2 right in front of the determinant. And equal to 2 times the determinant of the matrix A, B, C, D. And we know that the determinant of this matrix A, B, C, D is 7. So the answer is 2 times 7 equal to 14. That's the determinant of this matrix. The second matrix, A plus 3C, B plus 3D, C, D. What operation can we use to make this matrix look like this matrix here? For this matrix, if I multiply second row by negative 3, add it to the first row, what do I get? When I multiply a row by a constant, add it to another row, determinant stays the same. If I multiply second row by negative 3, add it to the first row. Second row stays the same. Negative 3 times C is negative 3C. Add it to the first row, I get A. Negative 3 times D is negative 3D. Add it to the first row, I get B. That's exactly the same as the given matrix. So this determinant is 7. So determinant of this matrix is 7. So determinant of this matrix is also 7. Next matrix. Negative 3C, negative 3D in the first row. 4A, 4B in the second row. Here we can see that 3 is a constant multiple in the first row. 3 is a constant multiple in the first row. So I can pull out negative 3 from the first row. I get negative 3 times C, D, 4A, 4b. Next, we can see that 4 is a constant multiple in the second row. So I can pull out 4 right in front of the determinant. So I get -3 times 4 times determinant of the matrix C, D, A, B. Now, compare this matrix with the given matrix here. We can see that everything is the same, but the rows are different. So what I can do is I can interchange row 1 and row 2. If I interchange row 1 and row 2, by the second rule here, if I interchange any two rows, the sign of the determinant will be switched. If I interchange any two rows, the sign of the determinant will be switched. So the sign of this determinant will be switched if I interchange row 1 and row 2. It becomes -3 times 4 times the determinant of A, B, C, D. And we know that determinant of the matrix A, B, C, D is 7. So the final answer is -3 times 4 times 7. Double negative is positive. 3 times 4 is 12. 12 times 7 is 84. That's the determinant of this matrix. Next, how can we find the determinant of the matrix? 4a plus 3c. 4b plus 3d. That's a typo. It should be 4b plus 3d. Phi C, phi D. What operations should we use to make this matrix look like this matrix here? So in the second row here, you can see that 4 is a constant multiple. In the second row, 4 is a constant multiple in the second row. I can pull out 5 right in front of the determinant. I can pull out 5 from the second row. I get 5 times 4a plus 3c. 4b plus 3d, c, d. Pull out 5 from second row. Next, I can multiply second row by -3, add it to the first row to eliminate 3c and 3d. I can multiply second row by -3, add it to the first row. When we multiply a constant to a row, add it to another row, determinant stays the same. Here, this number 5 will stay here. This number 5 stays in the front. I multiply second row by -3, add it to the first row. So -3 times c is -3c. -3c plus 3c can cancel. We get 4a. -3 times d is -3d. -3d plus 3d can cancel. We get 4b. C and d stays in second row. Next, we can see that 4 is a constant multiple in the first row. 4 is a constant multiple in the first row, so I can pull out 4. I can write 4 in front of my determinant. If I pull out 4, I get matrix A, B, C, D. And we know that determinant of the matrix A, B, C, D is 7. So the final answer is 5 times 4 times 7. 5 times 4 is 20. 20 times 7 is 140. That's the determinant of this matrix. Next, let's look at a theorem about elementary matrices. We know that an elementary matrix can be obtained by performing exactly one elementary row operation on identity matrix. And we know that there are 3 elementary row operations, which means E can be obtained in 3 different ways. Now let's look at the theorem here. Let E be an elementary matrix, which means E can be obtained in 3 different ways. If E is obtained by multiplying a non-zero constant k to a row in IN, then determinant of E equal to k. Part B, if E is obtained by interchanging 2 rows in IN, then determinant of E equal to -1. Part C, if E is obtained by adding a multiple of a row to another row in In, then determinant of E is 1. How can we prove that? How can we prove this theorem? Look at part A first. If E is obtained by multiplying a non-zero constant k to a row in In, then determinant of E is A, is k. How can we prove that? We know that according to the earlier theorem, if we multiply k to a row in a matrix A, if we multiply k to a row in matrix A, then the determinant of a new matrix is k times determinant of A. Here, for determinant of E, if E is obtained by multiplying k to a row in In, then determinant of E is k times determinant of In, according to the earlier theorem. When we multiply k to one row in In, the determinant of the new matrix is k times determinant of In. And In is identity matrix, which is a diagonal matrix, has 1 in the main diagonal. So determinant of In is 1, which is k. K times 1 is k. So determinant of E equal to k in the first case. If E is obtained by multiplying a non-zero constant k to a row in In, then determinant of E equal to k. Part B. If E is obtained by interchanging two rows in In, then determinant of E is In. According to earlier theorem, we know that when any two rows in a matrix are interchanged, the determinant of the new matrix is negative times determinant of the original matrix. So, if E is obtained by interchanging two rows in In, then determinant of E is negative determinant of In. And we know that since In is identity matrix, it has 1 in the main diagonal, zeros everywhere. Determinant of identity matrix must be 1. So we get negative 1, which is negative 1. So if E is obtained by interchanging two rows in In, then determinant of E is negative 1. Part C. If E is obtained by adding a multiple of a row to another row in In, then determinant of E is 1. According to earlier theorem, we know that when a row is multiplied by a scalar k and added to another row, the determinant of the new matrix is the same as the original matrix. When a row is multiplied by a scalar k and added to a different row, then the determinant of the new matrix is the same as the original matrix. If E is obtained by adding a multiple of a row to another row in In, then determinant of E must be the same as the original matrix. Original matrix is identity matrix. And we know that determinant of identity matrix is 1. So in the third case, if E is obtained by adding a multiple of a row to another row in the identity matrix, determinant of E is 1. That's a proof of this theorem. Next, based on the above theorem, we have the following corollary. If E is an elementary matrix, then determinant of E cannot be 0. The proof is simple. Let E be an elementary matrix. Then, according to the above theorem, determinant of E is either equal to k equal to negative 1 or positive 1, where k cannot be 0. Here k is a non-zero constant. K is a non-zero constant. So determinant of E is either k, negative 1, and 1. Since k is not 0, determinant of E cannot be 0. So determinant of E cannot be 0. Let's prove for this corollary. Next theorem, let E be an elementary matrix, and let B be any matrix of the same size. Then determinant of the matrix EB equal to determinant of the matrix E times determinant of the matrix B. Let's prove it. Since E is an elementary matrix, we know that E can be obtained in 3 different ways. E can be obtained by multiplying a non-zero constant k to a row in In, or E can be obtained by interchanging any 2 rows in In, or E can be obtained by adding a multiple of a row to another row in In. Since E can be obtained in 3 different ways, we must consider E in 3 different cases. Case 1. E is obtained by multiplying a non-zero constant k to a row in In. Then, by the previous theorem, we know that determinant of E equal to k. Also, since E is obtained by multiplying a non-zero constant k to a row in In, the product EB can be obtained by multiplying the same row in matrix B. The product EB can be obtained by multiplying the same row by k in matrix B. The product EB can be obtained by multiplying the same row by k in matrix B. Then, according to the earlier theorem, we know that when k is multiplied to a row in a matrix, the determinant of a new matrix is k times determinant of the original matrix. When k is multiplied to a row in a matrix B, the determinant of a new matrix is k times determinant of the old matrix. So, determinant of EB, determinant of the new matrix, equal to k times determinant of an old matrix. When k is multiplied to a row in matrix B, determinant of the new matrix is k times determinant of an old matrix. And we know that determinant of E is k. I can plug in determinant of E here for k. Hence determinant of EB equal to determinant of E times determinant of B. That's the first case. We prove that determinant of EB equal to determinant of E times determinant of B. That's case 1. Case 2. E is obtained by interchanging any two rows in In. E is obtained by interchanging any two rows in In. Then, by the previous theorem, determinant of E equal to -1. If E is obtained by interchanging any two rows in In, determinant of E is -1. Then by the previous theorem, determinant of E is -1. Also, the matrix EB can be obtained in the same way. The matrix EB, the product EB, can be obtained in the same way by interchanging the same rows. By interchanging the same rows in matrix B. According to earlier theorem, we know that if any two rows are interchanged, the determinant of the new matrix is negative times determinant of the original matrix. Since EB is obtained by interchanging any two rows in matrix B, then determinant of EB equal to negative determinant of B. Since EB can be obtained by interchanging two rows in matrix B, then determinant of EB equal to negative determinant of original matrix. Original matrix is B. And we know that determinant of E is -1. Negative determinant of B can be written as -1 times determinant of B. Hence, I can replace -1 with determinant of E. Hence, determinant of EB equal to determinant of E times determinant of B. That's the second case. If E is obtained by interchanging any two rows in In, then determinant of EB equal to determinant of E times determinant of B. That's the second case. Case 3. If E is obtained by adding a multiple of one row to another row in In, if E is obtained by adding a multiple of one row to another row in In, then by the previous theorem, if E is obtained by adding a multiple of one row to another row in In, then determinant of E equal to 1. So by the previous theorem, determinant of E equal to 1. Also, since E is an elementary matrix, the product EB can be obtained can be obtained by performing the same operation on matrix B. The product EB can be obtained by performing the same operation on matrix B. Which means EB can be obtained by multiplying a row in B by a constant and add it to another row. According to earlier theorem, we know that when a row is multiplied by a scalar k and added to a different row, the determinant of the new matrix stays the same. When a row is multiplied by a scalar k and added to a different row, the determinant of the new matrix stays the same. So in matrix B, if I multiply a row by a constant and add it to another row, the determinant stays the same, which means determinant of EB is the same as determinant of B. When we multiply a constant to a row and add it to another row, determinant stays the same. And since determinant of B is the same as 1 times determinant of B, determinant of B is the same as 1 times determinant of B, I can replace this 1 with determinant of E. Hence, determinant of EB equal to determinant of E times determinant of B. Replace 1 with determinant of E. I get determinant of EB equal to determinant of E times determinant of B. Since in all three cases we get the same conclusion, that means this conclusion, determinant of EB equal to determinant of E times determinant of B, must be true. Let's complete the proof. By cases. Next theorem. Let A be a n by n square matrix. Then, determinant of A is not zero if and only if the reduced rational form of matrix A is an identity matrix. How can we prove it? First of all, let R be the reduced rational form of matrix A, which means by performing some operation on A, we will eventually reach R. By performing some operation on A, we will eventually reach R. And we know that for each elementary operation, I can write it as an elementary matrix times matrix A. So I can first of all write it as E1 times A. Then perform the first operation. Then write it as E2 times the matrix. Then perform the second operation. E3, E4, until EK. Eventually, it will reach R. By performing some operation on A, it will eventually reach R. Since R is a reduced rational form of matrix A. So, if R is a reduced rational form of matrix A, then there exists elementary matrices E1, E2, EK, such that EK times EK minus 1, EK minus 2, E2, E1 times A equal to R. So here, if I take determinant on both sides of an equation, I have determinant of EK, EK minus 1, EK minus 2, E2, E1, A equal to determinant of R. Then, by the previous theorem, when we are taking determinant from the product of elementary matrix times another matrix, I can separate it right as determinant of an elementary matrix times the determinant of the matrix. So when we take a determinant for elementary matrix times another matrix, I can separate the determinant right as determinant of an elementary matrix times the determinant of another matrix. Since here EK, EK minus 1, E2, E1, they are all elementary matrices, then by the previous theorem, I can separate these elementary matrices right as determinant of EK times determinant of EK minus 1 determinant of E2 determinant of E1 times determinant of A equal to determinant of R. By the previous theorem, when we have elementary matrix times another matrix, I can separate the determinant using elementary matrices. Now let's prove the theorem. First of all, from left to right, assume determinant of A is not 0. Assume determinant of A is not 0. We know that determinant of elementary matrices can never be 0. By an earlier theorem, we know that determinant of elementary matrix can never be 0. Since determinant of EK determinant of E1 is not 0, determinant of E2 is not 0, and determinant of EK is not 0. And determinant of A is not 0. Since every term is not 0, since every factor here is not 0, then determinant of R cannot be 0. Since every factor here cannot be 0, it's not 0, then determinant of R cannot be 0. Their product cannot be 0. Since none of these terms is 0, then their product cannot be 0. Since determinant of R is not 0, then R doesn't have a row of zeros. According to an earlier theorem, we know that if a matrix has a row of zeros, then determinant of the matrix is 0, which means if the determinant of the matrix is not 0, it doesn't have a row of zeros. Here, since determinant of R is not 0, then it doesn't have a row of zeros. Since R is a square matrix, in a reduced Rorschach form, and R doesn't have a row of zeros, that means R must have a leading one on every row and every column. Then R must be the identity matrix. Since R is a square matrix in the reduced Rorschach form, and R doesn't have a row of zeros, that means R must have a leading one on every row and every column. Then R must be the identity matrix. So reduced Rorschach form of matrix A equal to R, which is identity matrix. Let's prove the statement from left to right. Next, we'll assume the right side and prove the left side. So Assume the reduced rational form of matrix A is an identity matrix. Then, since R is a reduced rational form of matrix A, then I can say that R equals to identity matrix. Hence, determinant of R equal to determinant of identity matrix, which is 1. So, I can plug in here. Determinant of R is 1. So determinant of EK minus 1 times determinant of E2 times determinant of E1 times determinant of A equal to 1. Since determinant of R is 1, then since determinant of elementary matrices cannot be 0, then I can divide both sides by these non-zero numbers. Then determinant of A equal to 1 over determinant of EK, determinant of E2, determinant of E1. Since these numbers are not zeros, are non-zeros, I can divide both sides by this number, get determinant of A by itself. And we know that 1 divided by non-zero number cannot be 0. 1 divided by non-zero number cannot be 0. That proves that determinant of A is not 0. That's a proof from right to left. So, determinant of A is not 0 if and only if the reduced rational form of A is identity matrix. That completes the proof of this theorem. Next, let me remind you of the equivalent statements. Equivalent statement says all these 6 statements are equivalent. If one of them is true, then they are all true. If one of them is false, then they are all false. Here, reduced rational form of A is identity matrix. That's statement 3 here. This is statement 3. Now, if I add one more statement here, called statement 7, that determinant of A is not 0. We know that statement 3 is equivalent to statement 7. If I add one more statement here, that determinant of A is not 0, by this theorem, we know that statement 3 is equivalent to statement 7. Since statement 3 is equivalent to all these 6 statements, and also we know that statement 3 is equivalent to statement 7, then statement 7 also equivalent to all these statements. We use statement 3 as a bridge. Statement 3 is equivalent to all these 6 statements, and statement 3 is also equivalent to statement 7. Then statement 7 is equivalent to all these 6 statements. So these 7 statements, they are all equivalent. If one of them is true, then they are all true. If one of them is false, then they are all false. And in general, keep this idea in mind. First statement says A is invertible. Last statement says determinant of A is not 0. They are equivalent. So keep the following idea in mind. We'll use it very, very frequently. Note, by the equivalent statements, A is invertible. A matrix A is invertible. If and only if determinant of A is not 0. A matrix A is invertible if and only if determinant of matrix A is not 0. We use this statement very, very frequently. Keep it in mind. Next, let's look at an example. For each of the following matrices, determine whether it's invertible. We know that by equivalent statements, if the determinant of a matrix is not 0, then the matrix is invertible. However, if the determinant of a matrix is 0, then the matrix is not invertible. So, in order to determine whether a matrix is invertible or not, we can find determinant first. Now, let's find determinant of matrix A first. Here, A is a 3 by 3 matrix. In order to find the determinant, we can find the coefficient expansion along any row or any column. And the sign of the coefficients is alternating. Plus, minus, plus, minus, plus, minus. Plus, minus, plus, and so on. The sign of the coefficients is alternating. Here, in the second row, since there's a 0 in the second row, I can try to find the coefficient expansion along the second row. It'll be a little easier since there's a 0 here. So in the second row, the sign is minus, plus, minus. So I get minus 3 times determinant of the submatrix by crossing out the second row and the first column. What's left is 4a, negative 16, negative a. The second entry is 0. 0 times everything is 0, so leave it the way it is. The third entry is 6, but the sign is negative. Negative 6 times determinant of the submatrix by crossing out the second row, third column. What's left is 2, 4, 4, negative 16. Then multiply. 4 times negative a is negative 32. Minus negative 16 times a is plus 128. Plus 0 minus 6 times 2 times negative 16 is negative 32. 4 times 4 is 16. Then combine like terms. Negative 32 plus 128 is 96. Negative 32 minus 16 is negative 48. Negative 3 times 96 is negative 288. Negative 6 times negative 48 is positive 288. Together is 0. Since determinant of A is 0, then we know that A is not invertible by equivalent statements. Next, for determinant of matrix B, doing the same thing, we can use coefficient expansion. Since in the first column there are 3 zeros, we can find the coefficient expansion around the first column. The sign in the first column is plus, minus, and so on. So I get 5 times determinant of the submatrix. I cross out first row, first column, that's a submatrix. 4, 9, 5, 0, 6, 9, 0, 2, A. The rest are zeros. Next, for determinant for this 3 by 3 matrix. For this 3 by 3 matrix, I can find coefficient expansion along any row, any column. Since in the first row, in the first column, there are 2 zeros, I can find the coefficient expansion around the first column. The sign in the first column is plus, minus, plus. So I get positive 4 times determinant of the submatrix by crossing out the first row, first column. What's left is 6, 9, 2A. I cross out the first row, first column. That's the submatrix. Then here, 5 times 4 is 20. For the determinant, 6 times 8 is 48. 2 times 9 is 18. 48 take away 18 is 30. 20 times 30 is 600. Since determinant of B is not 0, then by equivalent statements, B is invertible. Next, let me show you a theorem. Let A and B be square matrices of the same size. Then determinant of AB equal to determinant of A times determinant of B. How can we prove it? In order to prove this theorem, let's consider two cases. We know that for any matrix A is either invertible or not invertible. Let's consider this in two cases. Case 1, A is not invertible. If A is not invertible, then the product AB is also not invertible. Because according to a theorem we know in the earlier section, we know that if AB is invertible, then both A and B must be invertible. Since A is not invertible here, then AB cannot be invertible. So AB must be not invertible. Then, by equivalent statements, if A is not invertible, determinant of A must be 0. If A is not invertible, determinant of A must be 0. And since AB is not invertible, determinant of AB is also 0. Hence, determinant of A times determinant of B equal to 0 times determinant of B. Since determinant of A is 0, so I get 0 times determinant of B. And we know that 0 times everything is 0. And 0 equal to determinant of AB. So determinant of AB equal to determinant of A times determinant of B. So determinant of AB equal to determinant of A times determinant of B. So in the first case, if A is not invertible, we prove that determinant of AB equal to determinant of A times determinant of B. Now, case 2. If A is invertible, then by the equivalent statements, says that if A is invertible, then A can be expressed as a product of elementary matrices. If A is invertible, then A can be expressed as a product of elementary matrices. So by equivalent statements, there exists elementary matrices E1, E2, EK, such that matrix A equal to the product of E1, E2, EK. By equivalent statements, A can be written as a product of elementary matrices. So here, determinant of AB can be written as determinant of E1, E2, EK times B, because A is E1, E2 times EK. Then, according to earlier theorem, we know that determinant of elementary matrix times matrix B equal to determinant of elementary matrix times determinant of matrix B. So when we have an elementary matrix times another matrix, I can separate the determinant as determinant of elementary matrix times determinant of another matrix. Here, since E1, E2, EK, they are all elementary matrices, then I can separate it. I can separate this determinant as product of determinants. I can write it as determinant of E1 times determinant of E2 times determinant of ek times determinant of b. Then, since E1, E2, Ek, they are all elementary matrices, I can combine them together. Write it as determinant of E1 times E2 times Ek times determinant of B. And we know that E1 times E2 times Ek, that's matrix A. So I get determinant of A times determinant of B. Hence, I have determinant of AB equal to determinant of A times determinant of B. So in both cases, we get the same conclusion. Determinant of AB equal to determinant of A times determinant of B. Let's complete the proof by cases. Next, let me show you an example. Let A and B be 3 by 3 matrices. Verify that determinant of A times B equal to determinant of A times determinant of B. Is it true that determinant of A times A plus B equal to determinant of A plus determinant of B? Let's verify this. In order to verify these two formulas, let's first compute the product A times B and the sum A plus B, and then take determinants. For A times B, matrix A is a matrix 1, 0, 2, 1, 2, 0, 0, 1, 2. B is a matrix 1, 1, 0, 0, 2, 2, 2, 0, 3. When we compute the product, use row times column. Row times column. 1 plus 0 plus 4, that's 5. Row times column. 1 plus 0 is 1. Row times column. 0 plus 0 plus 6 is 6. Next, row times column. 1 plus 0 is 1. Next, row times column. 1 plus 4 plus 0 is 5. Next, row times column. 0 plus 4 plus 0 is 4. Next, row times column. 0 plus 0 plus 4 is 4. Next, row times column. 0 plus 2 plus 0. 0 plus 2 plus 0 is 2. Next, row times column. 0 plus 2 plus 6 is 8. Next, find the sum A plus B. A plus B 1, 0, 2, 1, 2, 0, 0, 1, 2 plus 1, 1, 0, 0, 2, 2, 2, 0, 3. And the corresponding entries. We get 2, 1, 2, 2, 1, 2. Second row. 1, 4, 2. Third row. 2, 1, 5. Then find determinant for A times B and A plus B. Determinant of the product A times B, we can use cofactor expansion. For cofactor expansion, the sign of the cofactors is alternating. Plus, minus, plus, minus, plus, minus, plus, minus, plus. We can take cofactor expansion along any row or any column. We can take cofactor expansion along any row or any column. Here, let me take it along the first row. So I get 5 times the submatrix by crossing out first row, first column. I get 5, 4, 2, 8. Minus 1 times, here the sign is alternating, positive, negative, positive. minus 1 times the submatrix. By crossing out first row, second column, I get 1, 4, 4a plus 6 times the submatrix. By crossing out first row, third column, I get 1, 5, 4, 2. Then compute the determinant for 2 by 2 matrix. I get 40 minus a minus 1 times a minus 16 plus 6 times 2 minus 20. 40 minus a is 32. A minus 16 is negative a. 2 minus 20 is negative 18. 5 times 32 is 160. Negative 1 times negative a is positive a. 6 times negative 18 is 10a, negative 10a. Then together, that's 160a, take away 108 is 60. That's determinant of AB. Next, let's find determinant of A plus B. Same thing, we can use coefficient expansion along any row, any column. Here, let me take coefficient expansion along the first row. The signs alternating, positive, negative, positive. So I get 2 times the determinant of the submatrix. 4, 2, 1, 5. Minus 1 times determinant of the submatrix. 1, 2, 2, 5. Plus 2 times determinant of the submatrix. 1, 4, 2, 1. Then compute the determinant for this 2 by 2 matrix. 4 times 4 is 20. 1 times 2 is 2. 1 times 5 is 5. 2 times 2 is 4. 1 times 1 is 1. 2 times 4 is 8. Then 20 minus 2 is 18. 5 minus 4 is 1. 1 minus 8 is negative 7. 2 times 18 is 36. 1 times 1 is 1. 2 times negative 7 is negative 14. 36 take away 1 is 35. 35 take away 14 is 21. So determinant of A plus B is 21. Next, let's compute determinant of A and B. Let's compute determinant of A and B. For determinant of A, I can find a coefficient expansion along any row, any column. Here, in the first row, we have 1, 0 here. Let me take determinant around the first row. The sign of the coefficient is alternating. So I get 1 times determinant of the submatrix. By crossing out the first row, first column, I get 2, 0, 1, 2. Minus 0, 0 times everything is 0. Plus 2 times determinant of the submatrix. By crossing out first row, third column, I get 1, 2, 0, 1. Then compute determinant for this 2 by 2 matrix. I get 4 minus 0. Minus 0 plus 2 times the determinant of this 2 by 2 matrix. That's 1 minus 0, which is 1 times 4 plus 2 times 1, which is 6. So determinant of matrix A is 6. Next, let's find determinant of matrix B. For determinant of matrix B, we can find coefficient expansion along any row, any column. Here, let me find it along the first row. The sign of the coefficient is alternating, plus, minus, plus. So this 1 times determinant of the submatrix. By crossing out first row, first column, I get 2, 2, 0, 3. Minus 1 times determinant of the submatrix. By crossing out first row, second column, I get 0, 2, 2, 3. Plus 0 times the determinant of the submatrix. But we know 0 times everything is 0. Next, compute determinant, find the determinant for this 2 by 2 matrix. I get 6 minus 0. I get 0 minus 4. Together, 6 minus 0 is 6. 0 minus 4 is negative 4. I get 6 plus 4, which is 10. So determinant of matrix B is 10. Then let's check. Determinant of A times B. Determinant of A times determinant of B equal to 6 times 10. Which is 60. 60 is the same as determinant of AB. So now verify that determinant of A times B is always the same as determinant of A times determinant of B. Now let's verify the second formula. Is it true? Determinant of A plus determinant of B equal to 6 plus 10. But determinant of A plus B is 21. They are not the same. Equal to 16. That's not the same as determinant of A plus B. So in general, keep in mind, in general, determinant of matrix A plus B is not the same as determinant of A plus determinant of B. In general, they are not the same. Determinant of A plus B is not the same as determinant of A plus determinant of B. Next, let me show you another theorem. If A is invertible, then determinant of inverse of A equal to 1 over determinant of A. How can we prove it? Since A is invertible, then by the equivalent statements, determinant of A is not 0. Also, since A is invertible, then inverse of A exists, and inverse of A times A is an identity matrix. Also, we know that both here, both A and inverse of A, they are square matrices. Here, both A and inverse of A, they are square matrices. An invertible matrix must be a square matrix, and its inverse is also a square matrix. Here, since inverse of A times A is identity matrix, if I apply determinant on both sides, I get determinant of inverse of A times A equal to determinant of I. What's determinant of I? Since I is an identity matrix, it has 1 in the main diagonal and 0 as other entries. Then determinant of I must be 1. We multiply all entries in the main diagonal, I get 1. Here, what's the determinant of inverse of A times A? According to the previous theorem, for any square matrices of the same size, determinant of A times B equal to determinant of A times determinant of B. So I can separate this determinant into 2 determinants. So by the previous theorem, determinant of inverse of A times A can be written as determinant of inverse of A times determinant of A, and that equal to 1. Then, since determinant of A is not 0, I can divide both sides of the equation by a non-zero constant. So, determinant of inverse of A equal to 1 over determinant of A. I can divide both sides of the equation by a non-zero constant. So the determinant of inverse of A equal to 1 over determinant of A. That complete the proof of this theorem. Next, let me show you an example. In the previous example, find determinant of inverse of A and determinant of inverse of B. In the previous example, we can see that determinant of A is not 0, so it's invertible. Also, determinant of B is not 0, so it's invertible. By the previous theorem, we know that determinant of inverse of A is 1 over determinant of A. And similarly, determinant of inverse of B is 1 over determinant of B. So, determinant of inverse of A equal to 1 over determinant of A. And determinant of A is 6. So the answer is 1 over 6. Similarly, determinant of inverse of B equal to 1 over determinant of B. And we know that determinant of B is 10. So determinant of inverse of B is 1 over 10.